So today we are going to discuss procedures in non-parametric when you have two or more samples. So the first testing procedure that I'm going to discuss is the Moods median test. So when it comes to the Moods median test, this is an alternative version for one-way and wine parametric. So in this case, your dependent variable should be a continuous one or a discrete one, and the independent variables should be discrete with two or more attributes. Since we can apply this to two or more samples, but I would like to encourage you to apply this Moods median test only for two samples, because when you have three samples, it's always better to apply the Kruskal-Wallis test because of the accuracy, because the accuracy of the Kruskal-Wallis test is always greater than the Moods median test. So if we look at the assumptions of the Moods median test, one assumption is the observations should be independent. That is, if you have two samples, the two samples should be independent and the observations within the samples also should be independent. And these observations should come from a population with continuous distribution function, and also the distributions of these populations should have the same shape. So if all these assumptions are satisfying, we can apply the Moods median test. So I would like to show you some examples where you can apply the Moods median test. Okay, before we go here. So let's say if you want to check the customer satisfaction, right? If you're working in a bank, we know in a bank you have different accounts. We have current accounts, we have savings accounts, we have children's accounts, right? So if you want to check the satisfaction, customer satisfaction level, whether there is any difference between the customer satisfaction level of these accounts, you can use the Moods median test. Or else, let's say if you are working in the industry and if there is a production line where the products are coming from, let's say, 3 machines. So you can, if you want to compare the machine time of these 3 machines, whether there is any difference between the median machine times, you can use this Moods median test. So talking about the procedure, when you are going to apply the Moods median test, the first thing that you have to do is, when you have several samples, 2 or more, first we have to pool all data. You have to put all the data together, and then you have to arrange them in ascending order, and you have to calculate the overall median value. So after calculating the overall median value, what you have to do is, we have to make a 2 into 2 contingency table and count how many values are from, how many values are greater than the calculated median, and how many values are less than the calculated median, and how many are coming from first sample and how many are coming from the second sample. Right, so I will example you this using an example, right? So if you look at this, this is the question type. So if you look at the question, it says a major wheat supplier is analyzing the yields of various crop methods. He randomly assigned 2 different wheat crop methods to a very high number of different acres of farmland and recorded the production rate, that is yield per acre, for each plot. Is there any significant difference between the crop methods that he used? So what has happened? There is a farmer who has cultivated a crop using 2 different methods. So basically you have to check whether there is any difference between these 2 methods, right? So the first task is, we can just write down what is our hypothesis. So what is our hypothesis? Our intention is to find out whether there is any difference between these 2 methods. So you can write down the mean yield of 2 methods are equal as your null hypothesis. The median yield of 2 methods are not equal as your alternative hypothesis. So once you write down this, so here we have our hypothesis, and then we can, what you have to do is we have to pool the data. As the step 1, we put the data together and arrange them in ascending order like this. So if you count here, you have 29 data points. So now we can calculate the median. So if you take the position of the median, that is we have 28 data points. So if you take the position of the median, that would be 28 plus 1 divided by 2, that is 29 divided by 2, that is 14.5. So you have to count and take the 14th observation and 15th observation. So according to this, that is 15 plus 15. So when you take the average, that is 15. So overall median for the pooled data set is 15. And now we are going to the contingency table. We have two methods, method 1 and method 2. So we have to check how many values are greater than overall median. So we can see our overall median is here, 15. Right? So if you count the number of values which are greater than overall median, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You can see there are 13 observations who are greater than the overall median. So you have to check within these 13 how many are coming from method 1 and how many are coming from method 2. Right? So by looking at the table, the original data set here, you can do that. So likewise, we have to check how many values are less than or equal overall median and how many are coming from method 1 and how many are coming from method 2. Right? So these are the observed frequencies what we get by looking at our data set. And then what you have to do is, then we have to calculate the expected frequencies. How we calculate the expected frequencies, right? So if you take this first cell as A, so the expected frequencies you can take here. If you look at the row total, that is 13. Here if you look at the column total, that is 14. So you have to multiply column total by the row total, that is 13 into 14, divide by the grand total, that is 28. So if you look at this cell where you have 9, the expected frequencies, row total 13, column total 14, the grand total 28. So 13 into 14 divided by 28. Here the row total 15, column total 14, so 14 into 15, grand total is 28, divide by 28. So likewise, we can calculate the expected value for each and every cell. So we have the observed values and we have the expected values. Now we can use the chi-square test. So for each and every cell, you have to take the difference of the observed value and the expected value. So as for an example, if you look at the first cell, the observed frequency is 4. The expected frequency is 6.5. So you take 4 minus 6.5, square it, divide by the expected value, that is 6.5. Likewise, you have to get the total, and you can see the chi-square test statistic is 3.56. This is the calculated test statistic. And now, since we have to read the chi-square table, we have to calculate the degrees of freedom. So the degrees of freedom is equal to number of rows minus 1 into number of columns minus 1. So you have 2 rows, 2 minus 1, 2 columns, 2 minus 1, 1 into 1 is equal to 1. Alright, so the degrees of freedom is equal to 1. So now we can look at the chi-square table. Right, so our degrees of freedom is 1 here, and our significance, right, degrees of freedom is 1, significance level is 0.05. So the chi-square statistic is 3.84. Right, we have 3.84 as the chi-square statistic, and table value. So we can see this one, the calculated test statistic value, from the table we have 3.84. This is greater than 3.56. So as the decision, that is, we cannot reject. If the calculated value is greater than the table value, you can reject H0. So here we do not have enough evidence to reject H0. So that is, we can conclude that the median yield of two methods are equal. Right? That's how we perform the Moore's median test. Right. So when it comes to two or more sample, as I previously mentioned, the Kruskal-Wallis test is the most accurate one. Right? So actually this is when we perform one-way ANOVA in parametric approaches, we need to satisfy the normality assumption. Right? So this is actually, we can replace the ANOVA by Kruskal-Wallis test. So when the normality assumption is violating, we can use this Kruskal-Wallis test. So the assumptions of this is as before, all the samples are randomly drawn from their respective populations and they are independent with each other, and the measurement scale should be at least ordinal. And the independence, that is, the sample should be independent with each other and within each sample. Right? Okay, so I will explain you the procedure. Here I have jotted down all the steps. So when you are studying, it is easy for you when you have all the steps. But I will explain the Kruskal-Wallis test using an example. So this is the test statistic that you have. So you don't have to by heart these test statistics. So in your examination, you will get all the test statistics. Right? So since we are going to apply this when you have more than two samples, you can take as the null hypothesis, let's say the median, you can take all the medians are equal as your null hypothesis, and as your alternative hypothesis, at least one median is different from each other. Right? There exists at least one median which is different. So that is basically the alternative hypothesis. So the decision rule, what you have to do is, you have to calculate your test statistic, and using the chi-square table, we read the table value. If the table value, if the calculated value or the test statistic is greater than the table value, you can reject H0. You reject H0 if the calculated value is greater than the table value. Let's see using this example. Okay, it says in a manufacturing unit, 4 teams of operators were randomly selected and sent to 4 different facilities for machine techniques training. After the training, the supervisor conducted the exam and recorded the test scores. At 95% confidence level, the scores are same in all 4 facilities. Alright, so they have chosen some of the employees, 4 teams, and they have given different training programs. So we need to check there is any difference between this training program or not. So here you have more than 2 samples. To check whether there is any difference between more than 2 samples, then here we go with the Kruskal-Wallis test. Right. So what is your null hypothesis? The distribution of the operator scores are the same, or the alternative one is the scores may vary in 4 facilities, right? So what you have to do is, When we are using the Kruskal-Wallis test, the first thing, we pool all the data and then we arrange all the data from we arrange all the data in ascending order. Right? You can see when you look at the data set, the minimum value is 51. So you have to give the rank as 1 to 51, and then the next minimum value is coming from facility 4, that is 52. So you have to give the rank as 2. So likewise, you take the data set, you pool all the observations, arrange them in ascending order, and you have to give ranks. So like we did earlier, if you have the same number, that is if you have tied values, you can average the rank value and give, right? And then after that, what you have to do is you have to check what are the ranks that you have received for each sample. For an example, if you take this first sample, the facility 1, for 88 we have the ranks 16, 82, 12, 86, 14 and 87, 15. And then what you have to do is you have to take the total of these ranks. So here 16 plus 12 plus 14 plus 15 is 57. Likewise, you have to take the total of the ranks of each sample. So here I have denoted that by T1. And now we are going to calculate our test statistics. So in one sample you have 4 data and you have 4 samples. So together you have 16 observations, right? So as your n value, Ni means the number of observations in one sample. So that is 4. Capital N is 16. So here 12 over 16 into 16 plus 1 is 17. And Ti squared. In first sample, Ti is 57. So you have 57 squared. And since we have the same number of observations and in each and every sample, you have to divide it by 4. So you take the squared values, 36 squared, 17 squared, 26 squared, minus 3 times n plus 1, that is 70. So here we can see when you take 17, right? That is when you take 17. When you substitute all the values, you get the test statistic as 9.77, right? So to find the degrees of the freedom, that is here you have how many number of rows? 1, 2, 3, 4 number of rows, and 1, 2, 3, right? You have 4 number of rows and you have 4 number of columns, right? So in the degrees of freedom you can calculate by using here you take the degrees of freedom is equal to, you can take number of rows minus 1 into number of columns minus 1. So in this case you have 4 minus 1 is 3, 4 minus 1 is 3, so that is equal to 9. So in this case there is a small mistake, the degrees of freedom is equal to 9. So now you have to check the chi-square value, right? So with 9, if you check this chi-square value, that is 16, this one is 16.92. So the chi-square table value you can write, that is the chi-square test table value is equal to 16.92, right? But here we can see our test statistic is less than 16.92. That is, we do not have enough evidence to reject H0. That is, there is no difference between these training facilities. So this one is wrong, the degrees of freedom and the chi-square value. So but anyway, you saw how to find the degrees of freedom and the chi-square value, right? Okay, and then right. Okay, so now we are going to discuss another area in non-parametric statistics, that is the rank correlation. In rank correlation means, now we know when you have two variables to find the relationship, we use correlation coefficient. So most of the times we are using the Pearson's correlation coefficient, but when we use the Pearson's correlation coefficient, what happens here is we have to in Pearson correlation coefficient, it always measures the linear relationship among two variables. But sometimes when you take two variables, there exists relationships. For an example, when you increase one variable, the other one is decreasing. Or when you decrease one, the other one is increasing. So they are not linear, but anyway there is a relationship. So in such cases, if you cannot apply the Pearson correlation coefficient, so we have different correlation coefficients that you can apply to such cases. One is the Spearman rank correlation, right? So in the Spearman rank correlation, what you have to do is in Spearman rank correlation, what you have to do is to calculate the correlation coefficient, you can use this formula. So you can see you have 1 minus d, or you have the parameters, you have two parameters n and di. So I will explain you how to calculate this Spearman rank correlation. Now if you look at this example, it says the table provides data about the percentage of students who have free university meals and their GPA scores. You have to calculate the Spearman rank correlation between the two groups, and then you have to interpret your results. See, you have the university name and the students, percentage of the students who are having free meals, and the number of students who have scored above 3.5 their GPA. That is, if you take university A, 14.4% of students are having free meal, and 54% of students have scored above 3.5 for their GPA. Now when you are going to apply the rank correlation, the first thing that you have to do when you are applying the rank correlation is you have to rank your data within each sample. You take first data set, right? That is the free meals. You have to apply the ranks. You can see the least value, or the minimum value is 4.9. So you have to give the rank as 1. So in red color, I have denoted the rank values, right? And here then you have, in the second sample, you have again the ranks denoted by red color, right? So from each sample you have to calculate the you have to rank the observed values, and then what you have to do is you have to calculate the difference between these ranks. So for an example, if you take 3 minus 4, that is equal to 1 minus 1, and then you have to take the square value. Why? When you look at this, see, you have to take the difference and square it. Alright, so what you have to do is 3 minus 4 minus 1, square it, plus 1. And when you take 2 minus 6, that is minus 4, square it, 16. 5 minus 3, 2, square root 4. 6 minus 1, 5, square root 25. 7 minus 2, 5, square root 25. Likewise, you have to take the square difference value. And if you have the square difference value, now you can apply this to the equation. How you are going to apply this? Now when you take the total of the square difference value, so here we have the total, right? And total is 76. So if you are going to calculate the correlation, that is 1 minus 6 times this summation of the square difference, right? That is 76, and then I have to divide by n, and here I have 7 observations, n into here n squared minus 1. So n is 7, 7 squared is 49, 49 minus 1 is 48. Right? Check the answer and see what is the correlation value. Right? 6 into 76, that is 456. Right? You have 456. Divide by 336 minus 1. So it is close to 0.36. Right? So the Spearman rank correlation between the GPA and the percentage of free meals is equal to 0.36. So you have to interpret your result now. So in the interpretation we can say that there is a weak relationship between the percentage of the free meals and the percentage of the GPA. Students who have scored more than 3.5 GPA. So when you are interpreting, it's the you can interpret it the value as in the similar fashion you are interpreting the Pearson correlation. So I think this will be useful when you have less number of data and when you have a non-linear relationships to find the strength of the relationship. Okay, and here in the Kruskal-Wallis test, there is a small thing that I have to correct. When you are calculating the degrees of freedom here, the Kruskal-Wallis test, the degrees of freedom is equal to number of samples minus 1. I'm really sorry, that is one of my mistakes. So here you have 4 samples, 4 minus 1 is equal to 3. So degrees of freedom is 3. So if you look at the chi-square table with 3 degrees of freedom, the chi-square value is 7.81. So that value is correct, 7.81, and you can see the table value is 7.81 and the calculated value is greater than the table value. So that is, we can reject H naught. That is, we reject H naught. That is, there is a difference between the training programs. So I think now it's clear how to use the Moore's median test and the Kruskal-Wallis test, and also how to find the correlation when you have non-linear relationships. So let's meet with another set of methods in our next